In the last two lectures, we calculated the pH and composition of two solutions composed of the most acidic form of leucine, H2L+, and the most basic form of leucine, L-. We've avoided running the calculations on the zwitterion, HL, because it's an amphiprotic species. It can behave as an acid or as a base, which complicates matters considerably. Let's see if we can find an efficient technique for calculating the pH and composition of a 0.0500 molar leucine solution. To do this, we'll need to use the Ka2 and Kb2 expressions shown here and think carefully about our approach. When we were considering the acid-base nature of ions and salts, we learned that a salt containing an acidic cation and a basic anion could be acidic, basic, or neutral. To figure out which it was, we had to compare the K values for the acid and base. The larger K value then controlled the solution's pH. The same is true here, except we're comparing Ka2 to Kb2 for the same compound. This comparison shows that Ka2 is larger, meaning that a solution of leucine, HL, will be acidic. However, the difference in the two K values is not large enough that we can simply ignore the basic nature of this amino acid either, so it's time to learn a new trick, using a charge balance. A charge balance means that you add the concentrations of all of the cations up and set them equal to the concentrations of all of the anions, as I've done here in step 1. Neutral compounds don't get to play because they didn't bring any charges to the playground. The challenge becomes finding some way to express the concentrations of every single species in terms of per ton, using the known chemistry of the substance in question. Let's start by writing out everything we know about this particular system. We are looking specifically for equations and equilibrium expressions that contain H2L+, L-, or hydroxide and hydronium ion, so that we can solve for everything in terms of protons. We can employ the Ka1 expression to solve for H2L+ in terms of hydronium ion. The Ka2 expression incorporates L- with hydronium, and the autoionization of water brings in a method for saying hydroxide in terms of hydronium ion. Next, we're going to solve each of the underlying species in the equilibrium expressions so that we can say them differently in the charge balance expression. Try this out on your own before advancing to the next slide. The result is that protonated leucine, H2L+, is equal to leucine, HL, times hydronium ion divided by Ka1. Deprotonated leucine, L-, is equal to Ka2 times leucine, HL, divided by hydronium. And hydroxide can be described as Kw divided by hydronium ion concentration. Let's take all of the results in the red box and drop them into our charge balance equation on the next slide. Try each of these steps before continuing to the next slide. First, make all of the substitutions from the red box into the charge balance expression. With the substitutions, this is the expression you should have. Next, we're going to clear all of the denominators, except for Ka1 in the first term, by multiplying every single term by the hydronium ion concentration. Make sure you got the same result shown here before moving on to the next step. Notice that we have the concentration of hydronium ion squared in both terms on the left-hand side of the equation. Let's factor that out next. The expression is starting to look a little more manageable. In the next step, solve for the concentration of hydronium ion. Admittedly, this does not look like a user-friendly expression. Let's use an algebra trick called rationalizing the denominator, then take the square root of both sides to see if we can clean this up a little bit more. Multiplying by Ka1 over Ka1 before taking the square root does make the concentration of hydronium in terms of leucine and our K values all fit on two lines. So that's an improvement, right? Now what do we do? Do we really have to plug in all of these values to solve for the pH? Or is there a better question to ask, such as, What color is my unicorn? If you're reading along in the textbook, you'll know this answer. Let's start by plugging in an easy number, the concentration of leucine, and see if we can make any simplifying assumptions from there. We see that the product of Ka1 and Kw is tiny, so we can ignore that since it will be much smaller than the product of Ka1, Ka2, and 0.0500 molar leucine. We see that the concentration of leucine in the denominator is also much larger than Ka1, so we can assume that value is small too. This amazingly simplifies the concentration of hydronium ion to the square root of the product of Ka1 and Ka2, since we wind up with the concentration times Ka1 and Ka2 over the concentration, just like we did in the last two lectures. Now we can get a super useful expression since all of the derivation is behind us. If we take the p function, or negative log, of both sides, we get pH is equal to 1/2 the sum of pKa1 and pKa2. You can breathe a large sigh of relief now. I will never make you derive that again. Going back to our original question, we can now solve for the pH. We can also use the negative antilog of the pH, 10 to the negative 6.036, to solve for the concentrations of H2L plus and L minus, respectively. It's worth noting that these values are both small and nearly equal to one another. This also tells us that nearly all of the leucine remained in the form HL.